Hello, everybody. Good morning, good afternoon, good evening, wherever you are joining us from. Thanks for tuning in. Great to have you here, and welcome back to the Polyhedra Show. So last week, we kicked things off with the zkML demo. It was a live demo with TC and Zhenfei, a really great use case for how our team is building infrastructure in verifiable AI. Then on Tuesday, we followed up with TC, our co-founder and CTO, and Sam, our CMO, to answer the first wave of questions from our community and to break down how zkML actually works under the hood. But the questions kept coming. So today we're back for part 3 of this series with Zhenfei. Needs no introduction. Zhenfei is our chief cryptographer, and Sam is back again to dive even deeper. So yes, we're going to be tackling the next round of community questions. I've passed through well over 2,000, more than 2,000 of these now. So thank you so much to you guys, our community, for being so engaged. You make my job super fun, and it's great to chat to everybody who DM me as well. Some really fantastic questions. So having said that, let's get straight into it. Thank you so much for joining us today, Sam and Zhenfei.
Thanks so much, Tony.
Thank you, guys.
Hey, Zhenfei, it's good to be here, man.
Yeah, great to be here.
I haven't got to do a show with you before, so I'm excited. So yeah, as Tony mentioned, we have some quick fire questions. I did this with TC on Tuesday, so we'll go for probably about 20 minutes, and these are all questions from the community. So the first topic we're going to touch on is architecture and integration. Can zkML work together with secure hardware like T's to make AI even more trustworthy?
Yeah, that's a great question. That's a question that's been heard a lot. To set up the stage, zk and T are not, so to speak, the competitors. They actually complement to each other. In most of the case where you use zk, like the rollups, like zk rollups, like zk VMs, you actually can use TE to ensure the correctness of computation also. So that's one side of the angle to look at it. The other side is the TE is still a centralized, trusted third party, meaning that you probably will need to trust the hardware manufacturer, and there will be master keys that's baked into a TE. Should your TE be broken, then all these things go vague. Whereas the zk itself, taking one step back, this is the comparison between zk and TE in general, not the zkML and TE with the machine learning. But anyway, so for zero knowledge proofs, you actually rely on mathematical assumptions. Hello, am I losing?
No, I'm here, man. I'm
here. Yeah. No, sorry, I just see
I'm concentrating on what you're saying.
No. I had network issues. So I'm just trying to confirm that I'm okay. So okay.
No worries.
So zk was like more like a mathematical ground truth. So if you trust math, and if the math says you can't break it, and then you're not supposed to break it. In terms of machine learning, I think as I said earlier, they are complementary to each other. You can use TE to argue the correctness of some of the computation also. I guess the challenge there was like the TE has a really limited memory. You won't be able to fit the large language models in one shot. We face similar situation in zk, but with zk we can do the segmentation tricks. Those are all the details. I get the short answer is they're complementary to each other. You can use both.
No, thank you, man. I love doing these shows because I get to learn from you guys as well. That was very helpful. Is zkML on Polyhedra easy to use with other popular zk tools like Halo 2 or Plonky 2?
Right. Well, I would say that first, we're not compatible with either because we are using a different arithmetization and a different proof backend. We wrote our own prover, which is called Expander. The reason is that the audience has already asked about Halo 2 and Plunky 2. Those two use a so-called Plunkish Plunk type of the arithmetization. It's not very good for machine learning. For machine learning, you want to use the so-called sum check based provers and the GKR provers. Just to give you an idea, for the like in machine learning, the most expensive operation is this matrix multiplication, so MATMUL. And to prove a MATMUL in Plunky 2 or in Halo 2, you need n squared of multiplication gates, right? Because you want to do the you want to implicitly write each multiplication for this vector matrix multiplication. For sum check, you actually just need one gate to be able to write the whole MATMUL gate. So one layer of sum check, you will be able to prove the whole MATMUL. That gives you like a gigantic, enormous improvement. So this is on the arithmetic. So we want to harvest this power. So we wrote our own sum check prover. It's called Expander. It's open source, so you can play it out and you can try. It's actually faster than Plunky 2 in many ways. Not only for the machine learning, you can also have a faster K-check prover. You have a faster Poseidon prover with our Expander prover. We are not. I guess what I'm trying to say is like we are not compatible with Halo 2 or Plunky 2. There will work to use Halo 2 to write a zkML. It takes like 100 hours to prove the same thing that we did in like 3 minutes. So please use us.
Yeah, please use us. I like that. All right, we're going to move on to demo and model mechanics. How are input commitments and model weights handled in this setup? Poisson hashes, Merkle roots, polynomial commitments.
Yeah, great question. We actually commit the models. Imagine a use case where you want to verify something on chain, right? So you are saying that okay, our inference is correct with regard to some model. Then how do we present this model to the verifier? You can't just you can't just give the model to verify in most cases, because model is supposed to be your trade secret or something. So you give a commitment to the model and show that okay, I actually use the model that this is committed to. And the side benefit of using this commitment, or polynomial commitment, is that it can be verified on chain.
No, nice. Thank you for explaining that. In polyhedra's zkML design, are the weights hard coded into the circuit, or do you support dynamic weight loading with integrity guarantees?
We have our compiler, so the compiler will generate circuit. So if you're using this committed weight that we talk, committed model. If you use polynomial commitment that we said earlier, then every time you have a new weight come in, then you will need to have a new commitment. So you will need a new kind of setup, but it's a one-time cost. So it doesn't allow you to dynamically load the weight while you are proving. There's another mode, which is like you do not commit to the model at all. Then in that case, you will be able to dynamically load the weight. I guess it's not a roadblock. It's not an essential problem. Like we can set up the scheme. We have set up the protocol that support dynamic weight loading, but it's not in most cases it's not optimal.
Yeah, no, makes sense. Makes sense. Do bigger or more accurate models make ZK proofs slower or larger? And how do nonlinear activations, ReLU, sigmoid, softmax get implemented efficiently? Right.
I guess the rule of thumb is like the bigger the prover, the bigger the model is, the slower the prover is, right? In terms that is true for both prover and verifier and the proof size. So obviously, if we are looking at a Llama 8B or 15B, then it's way bigger than say a CIFAR 10. So the second part of the question is like the nonlinear functions. That's a big challenge for us. We use this lookup protocol. So basically, we use lookup tables The specific algorithm for this lookup table is called lookup, which is actually the backend of lookup is GKR prover. So it's our we basically get two birds in one shot. Like we have the GKR prover that we built. It can handle the MACML, like I mentioned earlier. It can also build the lookup, which is used to handle all the nonlinear functions.
Okay. We're going to move on to performance, hardware, and scaling now.
Yes.
There's a couple of good questions here, actually. What are the current hardware requirements, CPU, GPU memory for running zkML proofs on advanced models like Llama 3? And how do hardware accelerators, FPGAs, ASICs factor in?
Right. So our current system the end-to-end system runs on CPU. We've benchmarked and reported data on the CPUs. We are working in progress on the GPU. We have implemented all the kernels in GPU and get some end-to-end improvement or performance for that, but we haven't integrated into zk PyTorch. This is our next step. And the biggest challenge is not actually about programming or implementing the scheme. The scheme itself we have implemented. It's more about scheduling, because as you can imagine, like in GPU, you have maybe you have limited memory, like maybe 36 gigabytes. That's already massive for GPU, but it's really minimal for desktops or for servers. So from between CPU and GPU, I think we should be able to have all this, and GPU we should be expect at least 10x improvement end to end.
Yeah.
For the hardware accelerators, FPGAs, ASICs, we do not currently work. We are not currently working on those. FPGA, I'm not very positive about it just because it's a performance per dollar issues. The ASICs that requires a lot of capitals to build ASICs, and we are seeking collaborators. If you guys are building it, then please come to talk to us.
Great. Yeah. So call out to anyone focusing on ASICs in the community. I liked this one. If real-time inference is needed, e.g. AI trading bots, how does zkML ensure low latency verification? Can you demonstrate proof generation and verification time?
Right. I think in the demo that TC showed last week, there was a time in the demo. So maybe we didn't stress it, but there was a timer.
Yeah.
Bear in mind that because we are running a demo in a Python script, it's a single thread and it's on CPU, so it's not very optimized. Just give you an idea, like you can actually prove it with sufficient time, like much faster than all the previous work. That being said, that is not a real-time inference, and we are working toward that. That is our holy grail. We are taking all the measures, like all the methods like the GPU accelerations, etc. And one thing that we have in mind is to use a distributed GPU computation to get further acceleration. Yeah, so I guess we are not sure. There isn't a clear path of how we achieve it. We just try all the existing method, and we hope that we're optimal, but we are not 100% positive at this current stage. We'll try our best to get to the real-time proving.
No, I got it, man. No, thank you. It's a race, and I'm glad we're winning it.
Yeah.
How performant is the demo today? Seconds, minutes, or hours for reference size models?
Right. Good question. So at the moment, what we can do is we can do the demo that we have done. I think it's around 10 minutes. So it's on the minutes side. The biggest model that we did was a Llama 7B, and that was we did 64 tokens in a batch, and that amortized for each token, it takes like 2.5 minutes. So if you do the math, it's like 2.5 times 60. So you get around maybe 2.5 hours to do the whole proving. But so we are like I said, it's it's way better than previous result, but we still have room to improve. And bear in mind, this is a single thread CPU, so moving from single thread to multi-thread, you get a 10x, and moving from multi-thread CPU to GPU, you get another 10x. So you probably will hope that with that we will be able to achieve real-time proving.
No, thank you for explaining that. We've got about 5 questions left. 2 on frameworks and developer experience. For ML developers without deep cryptography expertise, what's the learning curve for tools like zk PyTorch? What resources or frameworks does Polyhedra offer to ease integration?
Right, great question. I really enjoy this one because it's a low bar for me. So the goal for our zk PyTorch is to help people who does not know about cryptography to be able to deploy zk PyTorch or to be able to deploy zk ML proofs. So probably is a good. It will be good to review the demo last week. You will see that it's easy. Just add one more import from your PyTorch, and the rest it's done for it. The rest should be transparent to you, and if you find this if you find this UX still confusing, please let us know, and we try to make it as transparent as possible.
No, very cool. No, I love that as well. I mean, the access, the general access is so exciting from my go-to-market standpoint. Can you explain the role of Expander compiler in zkML and how it boosts the efficiency of zk proofs for machine learning inference?
Right. So the question is about Expander compiler, right?
Yeah. It's just explaining the role of the Expander compiler in zkML.
So yeah, we like underneath the hood there are like a few different tool chain that we're using. Like I can just go through the whole tool chain, so it might be easier. So you have a zk PyTorch, which has a ONX representation for the model that you have. These are all the classic AI part. So we extract ONX. That's a really nice intermediate representation. Then we use our compiler to compile it to some kind of a representation that's being that can be either read by us, by our prover. So this we call it zk CUDA IR. With zk CUDA IR, you put zk CUDA IR to our expander, it will generate circuit. So to the expander compiler, it will generate a circuit. So the expander compiler is basically you can view it as it takes the ONX and output a circuit. And then our backend expander is a prover that takes the circuit and generate proof. So that's the whole process.
No, very, very cool. Very cool. So we've got 3 questions left. And these are just about the real world use cases, which, I know that we're both very excited about to see some of these happening. But what are some potential real world use cases for zkML, like loyalty programs, privacy preserving, data analysis, or decentralized AI service? I mean, feel free to, talk about any potential real world use case you want.
Yeah, I guess we haven't really touched upon the privacy preserving data analysis or the anything related to the privacy very much. So I guess in the that's actually a real world use case that's been deployed already in real world. It's a real world application here, not some imaginary one. So it's a decentralized identification, right? So imagine if you are using Apple ID, what you do is like you scan your face and then you get authenticated. That's your UX. But what happened on the hood is like you have a chip or TE in your iPhone, and then which stores your feature vector of your face. And when you do the facial recognition, the camera will scan your face and then match and then run a model to extract a new feature vector and compare it with the one that's been stored in your trusted environment. So that's the classic way, or Web 2 way of doing it. The Web 3 way to do it, obviously you can't just store the your feature vector on chain, right? Because you will lose all your privacy. So what you do is like you store a commitment of your feature vector on chain, and then next you can't just compare it locally, right? Because that doesn't convince the third party. You won't be you don't want to use TE because it's centralized. We're in Web 3. So now we want to use a zkML, so the zk PyTorch or some, zk PyTorch. So you use zk PyTorch, generate a proof to showing that the inference is correct. So this is a one-time cost for a single proof, but then it can be used for future. So if you ever need an authentication and get verified on chain, you can use that proof. And this is also revocable in a sense, like you can when during your proof generation, you can also add the tags for lifetime, for purpose, etc. of this zk proof, and then so that when it gets used beyond its purpose, it will be invoked. So all this, and then it actually has been deployed by some applications, and it's really nice too. So that's, I guess that's one typical application that I want to advertise for today.
Great, man. Yeah, I think this is something that me and TC have discussed, and maybe you can debunk it again or give your input. Can zkML help protect AI model tampering or prevent hallucinations?
Right. Model tampering. So
they're two very different things, right? So
yeah. Model tampering and hallucination are two things. Yeah. Model tampering is, let's say, when you have a model and you want to prove that, you want to show that I'm using. Okay, sorry, taking one step back. So we all know that this week we have a very new GPT, like 04 something or some. The news was like OpenAI reduced their price for the 03 or something, right? And if I am a really bad actor here, I can just replace. To save my operation costs, I can just replace a 03 with a 02 or even a very low version. So that's model templing. So I provide this kind of service, but I claim to provide a good service, but instead I use a low quality service, and there's no way that you can tell without using machine learning, without using zkML. With zkML, you actually need to prove to the customer, okay, I'm using the very latest version that I charge you $200 per month. I'm actually using this prioritized model for your queries. Then prevent hallucination. I don't think we have a really good answer here. It's more about the model itself rather than the zkML. zkML only guarantees the correct inference of the model, but if the model itself is flawed, then we only prove the correct inference of a hallucinated model. So there isn't much thing we can do right now. We may be able to do things about proving the precision of the model later, but that requires more computation. And this is on our we are consistently thinking about it, but we do not want to act right now because it's going to take a lot of effort.
Yeah, no, thank you, Matt. Thank you, man. It's like, yeah, it's such a topical point at this stage in just mainstream consensus. So, I was on a call with an investor in Europe before this call, and yeah, I'm just grateful that we're on the right side of AI trust. He shared a figure with me that he thinks that by 2032, 10 to 20% of the globe, of the 5.7 trillion AI industry will be dedicated to trust compliance and privacy. So, you know, it puts Polyhedra in a pretty good position, I think. So that's all we have time for today. Everyone, Jen Fei and I are really busy cooking at the moment. We've got so much going on across from infrastructure, core infrastructure build to, you know, I'm working on several announcements that will be coming over the next coming weeks. So thank you, Jen Fei.
Thank you.
It's great to be here with you, man, and we'll definitely do this again soon. And thank you for Tony for introducing us, and for the community for being here listening today. So have a great Thursday, everyone.
Bye-bye.